Thanks everybody for joining this virtual workshop being hosted by AEC Tech. My name's Nate Miller. I'm the founder and CEO of Proving Ground. We're a digital design agency that works with architects, engineers, contractors, owners, and a variety of other folks in the building, design, and construction space to realize the potential for data and technology in their workflow. We sometimes work with folks on strategies, sometimes we help build software, do a bit of project consulting. And one of the topics that we've been investing quite a bit in as a bit of research and as an overall opportunity to make use of data is the topic of machine learning. And this workshop is really formulated around an idea of a workflow. There's a lot of hype around machine learning and AI. I think there's a lot of narrative and dialogue and no shortage of examples about how this stuff can be applied. In this workshop, we're going to get into some concepts related to machine learning, in particular neural networks. And then we're going to talk about how it can really serve to support a design and production workflow. So we're going to start to fold in different technologies as well. So Andy, you can go to the next slide. To kind of give you an idea of the flavor of the work that we've been doing over the years, we often build software, we build interfaces, ways to consume data, visualize it, and understand it. There's also a significant, we believe, change management component that goes along with these concepts. So not only is it important to recognize the capability of the software, but it's also important to equip people with skills and knowledge and different tools and methods that they can use to, I think, fully leverage these technologies. So you can go to the next slide, Andy. So machine learning as being the primary topic of this workshop upon which these other technologies and workflows will be anchored on can be defined any number of ways. There's a definition here on screen by Tom Mitchell that states a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. If its performance, let me move, I've got something over my window here. If its performance in tasks in T as measured by P improves with experience E. That's a fancy way of saying that the premise of a machine learning algorithm is based on the idea that it's a tool that can be used to process data and derive from that data a kind of function. So it's learning from training data, collecting this data over time, gaining experience, as this definition starts to state, in being able to measure some kind of variable or performance measure. And then as you feed it more data, it gets better over time. That's a very general description of this. And I think what you're going to see in today's workflows is how that kind of becomes manifest and how we start to integrate different concepts in a computational design workflow. We go to the next slide, Andy. There's a lot of narrative in popular media about AI and machine learning possibly replacing jobs, automating away jobs, performing creative actions. There's always an article that seems to come up pretty frequently. Variations of the same article: will machine learning or AI replace design? And one of the things I like to point out, and will become very apparent as we get into some of these examples, is that we tend to frame yet another set of tools that designers are able to employ. And the underlying assumptions that go into how you set up a neural network or a regression routine or a naive Bayes classifier impacts the outcome. And so it really does require designers to have a sense of how the technology and the outputs of this technology will match intuition. This is a comic I always like to reference from XKCD whenever we talk about machine learning. This is a set of regression plots using the same set of data. And it's starting to kind of suggest that, if your data is fuzzy and you are applying these algorithms to it, there could be many, many different ways to underfit or overfit the data that may yield good predictions or bad predictions. And you might need to calibrate and tweak your algorithm. I'm a pretty intuitive person when it comes to how I use technology. So I always like to take a look at my outputs and try to understand, does this match intuition or not? And then you can obviously do more quantifiable ways to validate the output of an algorithm, of course. But a lot of this very much needs to be under the control of experts and guided by, in some ways, our own experience in order to form how effective these tools can be. So you can go to the next slide, Andy. So we're going to be talking quite a bit about tools, and the stuff that we're going to be exposing you to is going to be very much based around Grasshopper and Rhino, and we've introduced and created a set of new components. We've done workshops in the past using LunchBoxML. Andy Payne, since joining our team here at Proving Ground, has expanded those plugins, and you're getting access as part of this workshop to a set of expanded tools that we haven't yet published out into the wild yet or promoted pretty heavily. So you're getting some pretty fresh stuff. These tools are built on the Accord framework. It's a .NET set of programming libraries that expose various machine learning algorithms for use in a computational workflow. And so on top of this framework, we've built, you can advance one, Andy, we've built an extension onto LunchBox called LunchBoxML. If you can go to the next slide, I believe. And so what we're doing is we're saying, okay, well, what if we could take some of these classes and methods that are exposed in the Accord.NET framework and then start to formulate a set of general purpose and reconfigurable tools that can be integrated into the computation workflow to help designers make predictions, process data, leverage those outputs for a variety of different purposes. We're going to be looking at a number of these components in this workshop, primarily focused around neural networks and how we can start to train a neural network, calibrate it, and then test against the neural network with some new data to create some kind of predictive scenario. So we can go to the next slide. A lot of the workflows that we'll be talking about are, we'll end up with algorithms that look like this or integrations that look like this, where we're able to, begin to stream in, inputs and outputs, train up an algorithm, look at different types of learning algorithms and activation functions. We'll be talking about hidden layers and hidden neurons in a neural network and different ways to calibrate iterations and so on. And then we'll be able to then test against this type of thing. So this is a brand new node. I think we published it just earlier this week. So go to the next slide. This is an open source project. So LunchBoxML, you can get access to the source code. Everything that you'll be seeing today in the course is published to the LunchBoxML repo. We haven't yet folded in the latest version of this into an official deployment with an executable, but it's certainly available to build from source at this point in time. So you go to the next one. Yep. So there's a number of different opportunities that I'll zip through here on how this might be used in different processes. There's, we have algorithms and components exposed for grouping and clustering, finding basically characteristics within a set of data, and then allowing the algorithm to start to group and cluster things. This is an example of using a k-means clustering or Gaussian clustering to find similarities in panels based on attributes. So we're able to feed, for example, in the characteristics of a set of panels, length, width, area, size, and so on. and then provide the algorithm with a kind of grouping criteria, and then it's going to attempt to cluster these things into similarities, and allow us to kind of explore perhaps opportunities for rationalization. It's pretty, I think, common use of one aspect of machine learning. You can go to the next slide. Feature detection is also another potential opportunity that we've used in our own work, specifically as it relates to point cloud analysis and looking at the features of a point cloud in order to discretize it into objects that can be modeled. So as many of you know, point clouds are extremely flat by nature. There's millions and millions of points. And we kind of see it as a common problem set that sometimes we need to actually derive modeled features from the point cloud. And so by using various clustering tools and classification tools with LunchBoxML, we can start to identify where, for example, in this case, where there are breaks between the componentry of a stone brick assembly. And in this case, we're going through and finding points that belong to different groupings, and then are able from those groupings to derive meshes and surfacing that describes the actual the real building component from this very flat set of data. You can go to the next slide. And this is one that was using kind of more of a predictive algorithm. I think it maybe in some ways gets closer to what we'll be talking about today. But it's looking at specification of furnitures and fixtures and spaces. So we're able to train an algorithm, for example, on the attributes of a given space, how the space may be used, and using historical data about, say previous offices that you've designed or other projects that you've been a part of, start to use that data, train up an algorithm to help create a predictive tool that can help you specify different objects based on this kind of historical record of experience. So you can go to the next slide. Today's workshop flow will cover a range of different technologies. There will be a heavy focus on the use of LunchBox at the start. We're going to be looking at LunchBoxML and components. Andy's going to start off with a lecture on neural networks. But we're going to then start to weave in a couple of other technologies that can be used in coordination with LunchBox. One is a tool called Semantic. Semantic is a data management tool that we've put out there. It allows users to define data properties on top of Rhino objects. It's meant to be kind of a flexible way to integrate data with your geometry, and also create reports and schedules of that data. And so we'll be using Semantic as a way to train and assign data using LunchBoxML as a backbone. Then we're also going to be talking about Conveyor. Conveyor is a Rhino to Revit workflow. And so what we really wanted to do, we're not going to go too deep into Conveyor, although we'll kind of be certainly suggesting how the workflow may be used. We wanted to kind of position it as a way to move data from one environment to another. So the idea being that, hey, I'm a designer, I'm working in Rhino, I'm using machine learning to help me make predictions about a design, I'm integrating that data on top of objects using Semantic, and then I'm going to be transferring the geometry and the data output from Rhino into Revit using Conveyor tools. To give you an idea of what we're after with Semantic in particular, we can go to the next slide, Andy, and the next one. Semantic is an interface for assigning data and scheduling information. So it's a dockable window that sits in Rhino. We can create groupings of parameters and properties that can be assigned to different objects. And then by having these properties assigned to objects, we can also perform live scheduling. And I use the term scheduling as derived from the Revit world, where you create a schedule of properties and attributes of objects. We wanted to create a lightweight version of that type of reporting as well in Rhino. So there's some parameters that you can assign and schedule with. You can also create formulas and build up this type of data integration with this. Go to the next slide, Andy. And kind of give you a preview of how this might work. It doesn't look like the videos are playing or streaming for me, but there we go. You can see like the idea of being able to select and assign objects, adjust different properties of objects, and have it impact reports is kind of central to the semantic tool. And by building up these types of this kind of structured data on top of objects, we're going to demonstrate how you can start to use this as a way to both train algorithms, but also assign outputs from machine learning algorithms that we're making in LunchBoxML. Next slide, Andy. And then Conveyor is the Rhino to Revit workflow that can consume those properties. So I think if you click through a few times, Andy, it'll kind of progress a set of slides. There you go. So the idea being that within Rhino, you have a variety of surfaces and types of geometries you can create. Conveyor provides a way to start to structure those freeform elements into objects that can be readable by Revit. And consume those into Revit as native objects, clean meshes, surfaces, and so on that can be used in the production process, all without kind of the need to use Grasshopper or kind of more complicated computational design tools that are often necessary in many of these workflows. We wanted to kind of create a more general purpose tool that might appeal to a wide variety of designers. So we'll talk a little bit about this. So with that, I'm going to pass the mic over to Andy Payne to talk about neural networks. One of the foundational concepts of this workshop will be to set up neural networks, calibrate them, use them in different ways. So Andy's going to start off talking about what neural networks are, and give a demonstration of the LunchBoxML neural networks. His role in many ways is also going to be to scare you a bit with some actual foundational concepts for neural networks, and then we'll talk about how they can be intuitively used and applied. So Andy, take it away.
All right, thanks, Nate. And thanks to AEC Tech again for inviting us to give a workshop. Before we get into the nuts and bolts, I just wanted to introduce myself a little bit. Again, my name's Andy Payne. I joined Proving Ground earlier this year. My background has been in architecture, but I have a doctoral degree from Harvard, which I finished in 2014, where I specifically was looking at machine learning and particularly neural networks to create intelligent, personalized, comfort-controlled for office spaces. So this is a domain that I feel like I know fairly well, and I'm excited to sort of explain it in a way that I hope will be clear and concise. I did have one question in the chat, which was whether or not this is going to be recorded, and I believe Amit can correct me if I'm wrong, but I believe it is already being recorded, and I assume that can be shared to the participants, just so you don't have to worry about recording it yourself.
That's right. We're going to record it and edit it and then publish out the link soon.
Okay. So like I said, we're going to try neural networks to you, and one of the powerful things I think about neural networks they've grown rapidly over the last decade, I think, primarily because they're very good at being able to train according to a set of be trained according to a set of training data. They're very good if you know what to expect, how to then train a model or a network to then work on data that it has not seen before. And I think that's a very interesting concept that machines and algorithms can begin to at least approximate the idea of learning by learning patterns and recognizing. And neural networks in particular are very good at being able to represent nonlinear functions or nonlinear data, as well as recognizing patterns. So in a lot of times, or in some examples, they're used for image detection, say in cancers and things like that, where you feed it in a new image to detect whether or not a person has cancer, and it's trained on thousands and thousands of other images that it's already seen of patients that have cancer, and it can then predict with a fairly high degree of accuracy whether or not a new patient and a new image set contains the same patterns. As I mentioned, they're very good and have very good training capabilities. And you really don't have to have, the network doesn't have to have any prior knowledge about the problem you're studying. There is a input-output mapping, meaning we have a sort of graph representation that describes the network itself. But that said, a lot of people have some confusion and tend to describe neural networks as a black box. The comprehensibility of what's going on in a neural network is sometimes convoluted. And for that reason, a lot of people dislike using it for some applications because they don't really understand what's happening underneath the algorithm or in the network. And so for that reason, I'm really going to try to explain in as clear a way as possible. You know, when we think about how neural networks have been taught over in the past, many times it has this correlation between a biological neuron and then how we can then equate what happens in a biological neuron where we have an input and some sort of response or output, which connects to other nodes or other neurons in a biological neural network, how we can then approximate that same function in a sort of mathematical term. And in many cases, this just becomes very confusing for most students. And so what I'm going to try to do is explain it in as clear and as simple of terms by showing you step by step what happens through a network, by passing real data, using a real example, and showing how the data flows through a network and how we arrive at a particular answer. So let's start by looking at a really simple example. And that is to say, can we use a neural network to predict thermal comfort? And so what we want to do is be able to take a set of data and determine, make some measurements, for example, and determine whether or not someone was comfortable within a given temperature zone. So let's say in this hypothetical example, that we took some measurements in the morning that showed, fairly cool temperatures in a room, and we asked an occupant whether or not they were actually comfortable in that space. And in these particular examples, the occupant reported that they were not comfortable. We then took some more measurements around lunchtime, and the temperatures were a little higher. And in this case, all the occupants, or this particular occupant, reported that they were comfortable in this particular temperature zone. But then later in the afternoon, we took some more readings, and again, from solar heat gain or what have you, the temperature was hotter, and the occupant again reported that they were not comfortable. So we have this graph of data that explains, in some instances where it's too cool or too hot, you have a situation where an occupant might not be comfortable. And then other instances in the middle where they are reporting that they are comfortable. And if we wanted to use this data to make a prediction, we can't simply just fit a straight line to the data and try to make a prediction, because if we were to do that, no matter how we try to rotate that straight line, it can never really accurately predict any more than 2 of the 3 states, right? And what we really need to do is have a curve, or be able to fit a curve to the data, so that if we were to try to use that curve as a predictor of whether or not someone was comfortable or not, we could simply take the x-axis and plot it on the curve and determine whether or not someone was comfortable. And this is what neural networks are particularly good at, is being able to fit data to nonlinear, or fit curves or to nonlinear data. And I think that's what we're going to try to show through this example. And really, the other powerful thing is the data can be very messy, or let's say chaotic in some instances, and neural networks still perform relatively well, even in these complicated or chaotic data sets, because they're very good at being able to break down the data and begin to fit curves to different sections and be able to map those together. And so that's really what we're going to try to show today. So we're going to show how, in this today's workshop, how we can take something that looks like this and show how the output of this can begin to fit a curve to the data set. And so what we're going to do is explain a couple of the preliminary terms of what we're even looking at. So in this very simple example, we have a set of nodes. In this case, we have an input node, an output node, and 2 intermediate nodes. And the connections between those nodes are just simply called connections. And we have network parameters along those connections which begin to describe and weight the inputs that go into these middle nodes, which are called, have something called an activation function. And those activation functions are really the key to how these neural networks function, because what we're going to do is learn that according to these network parameters, we can take sections of these activation functions and add them together to make a more complex curve as the output. And so we're going to show exactly how that works. So what is an activation function? Well, it's a function. It's an equation, if you will. And there's really many different types of activation functions that are available. One that is very commonly used is something called a sigmoid function, which looks like this. And you can see it basically spans from 0 to 1. It also has this little value called alpha, which essentially controls how steep the sigmoid curve is. So when you see the sigmoid alpha in the grasshopper node, know that that's controlling the steepness of this curve. So a higher number begins to make this look more up and down, vertical. We have something called a bipolar sigmoid, which is pretty much the same function. It's just scaled, instead of being from 0 to 1, it's scaled to go between -1 and 1 along the y-axis. There's other activation functions that can be used, like a threshold activation, which is essentially a piecewise or stepwise function to say you go immediately from 0 up to 1, and there's no sort of intermediate change. There are linear activation functions. Again, that alpha begins to control how steep that linear curve is. It's just a scalar value that controls the steepness of the activation function. These are the activation functions that are available. There's another one called rectilinear, rectified linear, ReLU sometimes. These are the ones that are available in the Accord framework. But there are a number of other ones. If you were to Google activation function, you will find a host of different types of functions that can be used in training a network. And I believe that slide went a little fast, but one of the things that we're looking at is that in this particular example, we are trying to do about as simple of a network as possible, in which case we are showing just a single input node, 2 intermediate nodes, and a single output node. But in reality, what you're more used to seeing is a graph that looks something like this, where you might have 1 or more input nodes, and this is called your hidden layer. You're going to have 1 or more output nodes. Again, this is your output layer. And any number of neurons that are located in the middle between these, which are your hidden layers. And your hidden layers, you can have multiple hidden layers if you want. Let me just see, I think I have a chat request, or if you guys want, since I can't really respond to the chat, just feel free to ask your question. I'm happy to answer, stop the discussion and answer any questions if anybody has one, if I'm going too fast or too slow.
Yeah, so maybe what you can do is, after you get through your first set of slides, we can collect questions and then return to them.
Okay, sure. So the connections between all of these networks, again, are just these connections between the nodes. But what we're going to try to do today is, in this really simple data set, is to look at about as simple of a network diagram as we can, which is a single input and a single output and these activation nodes, to try to determine how we can predict thermal comfort. And for simplicity, what I'd like to do is to normalize the data set. So instead of using the numbers that we have for temperature readings, which are spanning between 62 and 86 degrees Fahrenheit, I'd like to do is just simply normalize those to run from 0 to 1. And I think that'll make our numbers go a little bit cleaner and make the math a little bit easier. The other thing we're going to do is, for now, we're just going to assume that we have a given set of values for these weights and biases. These weights and biases, I'm going to explain how these numbers get resolved a little bit later. But for now, let's just assume that we have these numbers, these parameters assigned, and we're just going to see how, if we were to feed data through this network, how it begins to resolve to approximate that curve to fit the data. So the first thing we want to do is we want to actually plot a value, an input value, as if we were determining what is the prediction if we were to try to feed in a value of 0, a normalized temperature value of 0, which again is mapped to about 62 degrees. If we were to feed this through, the first thing we encounter, we're going to feed it through and pass it up to this node up here. The first parameter that we encounter is a multiplier. In this case, it's that weighted value that we talked about. And all we're going to do is take that value and multiply it by 44.74. We then take that value and we hit another number. In this case, this is an addition. We're going to add to it the bias factor. In this case, it's negative 29.71. So our algorithm looks something like this, where we're going to take our input value, multiply it by our weight, and then add to it the bias. And what that tells us is it's going to become the x-axis coordinate in our activation function. So if we do the math, 0 obviously cancels out our weight value, and the value that we end up coming in with is negative 29.71. So we can map that directly onto our activation function. Now, what is our activation function? Again, in this particular example, I've chosen to use a sigmoid function, but you can choose any type of activation function depending on the type of data that you're using. But for the sigmoid function, we have 1 over 1 plus the log of our x value times the alpha. So if we were to just, again, to simplify the math, we feed that through, and we end up with a value of 0.99. So what we can do is take that value and plot that on our y-axis here. So again, we had an x value of 0 input, and we'll plot the y value that's output from our activation function. Now, if we do that same process again, only this time using a value of 0.1, we can go through the math again, and again, our output value is 0.99. So let's just do the math very quickly and step through these values going from 0 to 1 so that we can plot these values. And now what we can see is that, yes, they start out all being about the same value of 0.99. But as we begin to pass the data through this data set, or through the network, you can see it begins to get values that form a curve that looks something like this, right? So the data that gets fed through the first part of this activation function forms a curve that looks approximately like this. So now what we're going to do is go to the other side of the network, and we're going to do that same process that we did before, which is to take, our input value of 0. We're going to multiply it by its weight, in this case 36.91. We're then going to add to it the bias. In this case, the bias is negative 11.41. And then that becomes the x-axis coordinate of this activation function. Again, we can then do the math, the zeros cancel out, and we're left with negative 11.41. If we pass that through that same sigmoid function that we just did before, again, our output value is going to show up as 0.99. So we're going to do that same process that we did before and pass through new data going from 0 to 1 so that we can track through and see how this data is fed through the network and how it begins to get processed through the activation function. Now you can see these points form a different curve. In this case, we get a curve that looks something like this. They're very similar, but they've been offset, as you can see, based on the weights and biases. Now, the next thing we're going to do is pass the data back through so we can go to the output, and we encounter a weight that is -1, right? Another multiplier, but in this case, it's -1. And you're probably asking yourself, why didn't I do that same thing over here? Well, in this case, this one has a factor of +1, in which case it doesn't really affect the data at all. So I'm not really going to have to do anything on this side. But in this case, we have a weighted value of -1. So what that does is essentially you can take each y-axis value and multiply it by -1. In this case, our value was 0.99. So now it moves down to here to be -1. And we can do that for all of the data, which is essentially flipping that curve along the x-axis, right? So we just multiplied by the weight of -1, which has flipped that pink curve so that it's now along the bottom. And now you can see the next stage through the network is that we have to add both sides of the both values that are coming in to this summing node. And this summing node begins to add up all of the values in both of the graphs together. So if we have a +1 on one side and a -1 on the other, those two cancel out and we get a value of 0. Again, we can do the same thing for all of the intermediate values. And now you can see what happens is we get a curve where we add both of those curves together, which then makes a composite curve, which is that green curve. In this case, the green curve is exactly what we were trying to achieve, that fits the data as closely as we could. We can do a check here and feed in new data. In this case, let's say we had a value of 71 degrees. If we normalize that, we get a value of 0.45. We can pass that data through each of these functions just like before, and what our numerical output is will be 0.98. Another way to think about that is to plot this value on the x-axis and then determine, based on our curve data, what the y value is. And if it's close to 1, then we can make a prediction that that occupant at 71 degrees would be comfortable. If it was closer to 0, obviously we could make a prediction that the occupant would be not comfortable. And that's basically it. That's how a neural network works. We feed data through the network. Each time it encounters a new node, particularly in the hidden layers, it's going to be multiplied and added. So the first thing it does is it gets multiplied by a certain weight. It then gets added a certain level, which is called the bias. And together, those network parameters slice and flip and stretch the activation functions so that you end up getting a new shape that approximates the data, right? And so that's really the power of networks. And so you can imagine that this is a very simplified example with only 2 nodes. You can imagine what happens when you get a much more complicated network structure where you might have multiple hidden layers, each with a large number of hidden neurons. The type of curves that can be used or created to fit the data can be quite complex. But it's also very good at being able to create curves or surfaces that can fit the data in a very robust way. So you're probably
maybe this might be a good point to ask the question that is in the chat.
Okay.
And that is, on what basis does one select the activation function?
Okay, that's a good question. Again, it's kind of about knowing. It's kind of two ways. One is knowing a little bit about the input data that you're using. So is it a continuous type of data where you have data that's running the gamut between, say, a certain level of, say, between 0 and 1, or -1 to 1, +1, or is it, say, only a binary set of data between 0 or 1, right, with no intermediate levels? So depending on the type of data, if it's a binary condition, you might choose a threshold activation function, right, where it's only 0 or it's only 1. But if you have a continuous set of data where the data is coming in as the input or the output, the expected output is going to be, anywhere, it could be anywhere in between 0 and 1, you might choose a sigmoid or any type of data. It really comes down to having a feel for the data. And I think that's where Nate was getting at the beginning, which is to say, I think we have this fear that AI and machine learning is going to automatically replace all of us. But that's really probably not the case, in that it still requires a finesse and a knowledge from the user, in this case, you guys, a knowledge of what type of data you're putting in and how that data was created and or collected and what type of data is it really, and then how you can begin to use that data and the different parameters in the network, which again, we've only introduced weights and biases, but there's going to be other terminology that I'll introduce in a minute, which again, all these things together are things that you can't just hit a button and train the network and have it do exactly what you want. There is a little bit of trial and error. And the more that you know about the data and the more that you know about how these parameters work and how the networks work, the better understanding you can have to make the right assumptions and the right tweaking of those values, because there really are a number of different parameters that you can change that have a profound impact of how well the network performs. Did that answer the question?
I think
Again,
so. I think that's a great. I think that's a great explanation. Great. Yeah. They said that. Yes, that makes sense.
Okay. Yeah, I'm used to being in person, so I'm used to reading the room a little bit. This is a little.
You can't tell if people are nodding along or shaking their heads.
That's right. So again, we talked about those weights and biases, and I just assigned values based on that particular example to explain how the networks work. But the question is, how do we determine what the optimal numeric values for those parameters would be so that we could get the optimal fitted curve, right? And so that's a big question with networks. And again, we need to kind of cover some of the basics, which is to say, we need to know that there is something called an input layer, which can have one or more nodes, a hidden layer, which can have one or more hidden layers, which each contain their own number of neurons, and an output layer, which again can contain one or multiple nodes in it. What we first do is assign randomly the weights and biases to the network. Once we assign those values, we start to feed it in training data. This training data is data that has inputs and outputs. So you need to know with this training data, what is it that I'm feeding in and what is the expected output? For example, just a very dumb hypothetical example would be adding two numbers together. Could you create a neural network that could predict the addition of two numbers? That would not be very good because it's a linear output, but essentially what we have are two inputs and a known output. If you feed A as the input A as, or in this case, X is 2 and Y is 3, we know the output is going to be 5, right? So we know the inputs and we know the expected output. And that's important in developing a set of training data to train these networks, is that you have to have some known input data and what the expected output would be. So what we do is we first randomly assign some values to the weights and biases and feed that data through the network, and we come up with some value. This is called the forward pass. Now we need to know how accurate is our output value, right? We need to have some way to determine what is a score or how well did our network perform with this data. Right? So we fed through the data and we came up with a value. How close is the value that it computed to what it was trying to achieve? And so the way we do that is, there are a number of different ways, but a very common way you can do that is something called the mean squared error. And all that is a fancy way of saying you're going to try to compare the computed output to what was expected. So you're taking the difference between the computed output and what was the expected output. So again, as I mentioned, if you have an input of 2 and 3 and you know the output should be 5, we need to compare what was computed versus what it expected, right? So we're just doing a subtraction and then we're squaring it so that we can know that the output value will always, the error rate, let's say, will always be in the positive domain. And the mean and square error, all that means is that if you have 500 iterations of this training data, it's going to take the average of all of that training data and give you the average of the square of the errors. That's basically what that's going to equate to. And we're going to call that the cost function. which is essentially telling you how well did our network perform based on the current values of the weights and biases at each node. So to find the most optimum parameters, we need to use something called backpropagation. And backpropagation is the process of repeatedly adjusting the weights and biases so that we minimize the difference between that computed and expected values, right? So again, one of the key words in this definition is to minimize, and then the last part is simply describing that cost function that we just described. So all we're trying to do is minimize the cost. And to do that, we need to find something called the gradient. The gradient is essentially a derivative, but a gradient simply shows us how much a parameter, in this case the weight or the bias, needs to change in either the positive or the negative direction so that we can minimize the cost, C, right? So that's basically all we're trying to do, is to go backwards through the network. So in this case, what we're going to try to do is use this function here. And this is for the weights, but the same can be for the biases, where we have the weight at a given neuron. This part is called the partial derivative, which I'll explain a little bit more in a second. But essentially, it's the partial derivative of the cost with regard to the weight, and that's known as the gradient. And then we have one scalar value that's also assigned called the learning rate. So as we go backward through the network, what we're doing is we're going through and solving for this equation at each node. We're solving for this equation, which tells us how much to adjust each of the weights and each of the biases, so that the next time through that we pass data through, the computed value becomes a little bit closer to what we expected. Hopefully that makes sense. And this is called the backwards pass, or back propagation. This is where the name comes from. If we wanted to look at this a little bit differently, this equation that talks about the weight minus the epsilon of the partial derivative, let's look at this in a slightly different way, where we're graphing, in this case, the cost with regard to the weight, right? So we have this function, a parabolic function, that describes the cost with regard to a single weighted value. And at first, we're going to start off by randomly assigning this weight a value. And what we want to do is to find a tangent line at that point. So those of you who remember pre-calculus probably remember that the slope of a tangent line is simply the change in y versus the change in x, right? And that's what we're talking about, the partial derivative, is this change in y over the change in x. You'll notice that my y-axis is the cost, the x-axis is weight, which essentially equates to here. This is that partial derivative here, is the change in cost over the change in weight. So this tangent line begins to explain sort of the direction we need to move this weight so that the cost can become lower or closer to zero, right? So we simply do the math here. Have assigned values in this hypothetical condition. And what we end up getting is the slope of the tangent line is a positive value of 4.22. Now you could say, why don't we just set the weight of that neuron to be 4.22 and be done? Well, that wouldn't necessarily be the right way to go about it, because we really don't know if this minimum, if we have multiple weights, if this minimum is going to be the minimum of the global shape of the data, right? What we're trying to do is achieve the global minimum. So we really don't know. There could be multiple local minimums. Also, there could be lots of different weights in our network, right? And so this is not a trivial calculation to do when you start to scale up the number of nodes in your network. So really the best possible solution is to actually take a small step in that direction. And then as you begin to do it over time, you can, this value will approach zero. So you don't make one large step, you take many small steps. And hopefully over time, you start to move towards a global minimum, if that makes sense. So this is where that learning rate comes in. So we've just found the partial derivative. Now what we need to do is multiply it by the learning rate. And this learning rate is just a scale factor, in which case we say we might want to multiply it by 0.1. or even 0.01. So instead of being a positive value of 4.22, it's now gonna be 0.42. So we're just taking a small step in that direction. However, if we were to move in that direction, we would be moving away from the minimum value of 0. You'll also notice that we have a negative. We're trying to subtract this value from the weight. So what that does is it inverts that value and we move closer to 0. Now, if we follow that process over and over through the training data, at each time, what should happen is the weights begin to become adjusted so that the cost becomes closer to 0 over time. And that's really what we're after. This is the most simplified way of explaining. There are a number of different ways you can adjust the weights, but the most common way is something called gradient descent. And it's called gradient descent because you're solving for the gradient and it's descending towards 0. You can imagine it as a ball that's rolling down a hill. You're trying to find the ball where it rolls down to the lowest point in your data. And so this process of iteratively optimizing the weights is called gradient descent. And so as we train our neural network, the weights and biases get adjusted so that the difference between what we computed and what we expected will become much smaller. It gets closer and closer to 0. And that's really it. That's all that neural networks do, is that as we feed it in this data, we're trying to adjust those weights and biases through the network so that what we get out of it should be very close to the approximate value that we had expected.
A question in the chat. Is there any check one can do to investigate that after training to know whether the model has achieved local minima or global?
There are some methods that are out there. We have not implemented any of them in here. There are some things called cross-validation, which is a method of breaking up training data into something called folds, and then feeding that through and determining whether or not the parameters, basically breaking up the training data into a certain subset of categories. So you can say, let's say we had input data and we wanted to break it up into 10 separate groups. And we're going to assign the first 9 groups as our training data, and the last one will be our testing data. And so we feed that through and we determine how well that works. Now the next time we're going to do it, the last one is not going to be our testing data. Maybe the first one's going to be our testing data and the last 9 are going to be the training data, and so on and so forth. So you break up the data into smaller subsections and then you feed that through. And as you're doing that, it basically optimizes all of the weights because you're essentially training it many, many different times. And then from the composite of those values, you should be able to determine the optimal weights of your network so that you get the most optimum solution. And so there are papers out there, and someone's actually talking about training and testing splits. And that's exactly where we're going with this, is that you can actually create training and testing splits. And that's essentially what cross-validation is setting that up so that you can train the data on multiple different types of data, or train the network on multiple types of data, and begin to understand how the composite of those weights give you the best output, if that makes sense. We're also going to talk about how you can begin to look at overfitting data as well, because as I mentioned, overfitting data is where you design a network and it works really well on the data that you have trained it for, but when you give it something it hasn't seen before, it doesn't perform very well. And we're going to look at an example of that in a little bit. But essentially, neural networks do have a problem in that they can tend to overfit the data. And like I said, what that means is it's very good at making a prediction if you've already given it something it's already seen before. But if you are wrong, if you give it something it hasn't seen, it might not make an accurate prediction. And what you're trying to do is create a model that can make very good predictions, even on data it's never seen before. There's different rules of thumb. There was a question about the training splits, about 60, 25, and 15. It's really, I've seen different numbers for different splits. And so you can, I don't know that I have a good number for you to say whether it's 16, 25, and 15% as your training testing split. There are different numbers. I've seen 10% as testing, 10% validation. And so you can do different numbers. I think it's really, again, as you begin to look and play around with neural networks, you're going to see that there's a lot of different parameters, and just small tweaks with those parameters have a pretty profound impact about how well a network's going to perform. And so it really does take a little bit of practice and trial and error to do that. And yes, there are a number of papers. This is really just a basic introduction to neural networks. There are some people who are looking at how you can auto-tune neural networks so that it's sort of what we're talking about here. Are there optimization processes that you can use that will sort of automatically try to find the best possible solution based on the data? But in my opinion, I still think the data scientist, if you will, or the architect, or whoever is developing the training data and the network, really has a responsibility to understand and understand the data and what these parameters mean, so that they can try to make the best assumptions while they're training the data. I hope that answers the question to some degree. Let's simply recap, because I think I'm almost done with this set of slides, and then we can jump into the example. And so to recap, really what I want you guys to walk away with is a basic understanding of how neural networks work. To do that, we need to know that each neural network or each node in the neural network has some network parameter assigned to it along the connection, which is called the weights. And these are the ones that we multiply. So a weight is multiplied by the input value. And then we add to it a certain bias value. And this bias is simply shifts whether or not you're moving along the x-axis or not. Together with the weights and biases, they begin to essentially take subsections of a activation function and begin to either flip or stretch the activation function that you've chosen into shapes that can be then composited together to fit the data that you've assigned. As you get more complicated network structures, the optimization process that you do is you have to come up with a set of training input and output data. This is called supervised learning, where you're simply supervising the learning process by giving it what is the input value and what should be the expected output value. So at the beginning of this optimization process, we feed the values through. The weights and biases are randomly assigned. And at first, the computed value will be very off. You can imagine if these are random values and we're trying to add 2 plus 3, we might get a value of 8 or something even worse. And so at first, the values are going to be very wrong. However, we then reverse this process by going backwards through the network and calculating the gradient at each of those nodes to determine how to adjust the parameters so that the next time through next time we pass the data through, the computed value will get closer to the expected output. So again, over time, these parameters get adjusted so that the error or the cost approaches 0. Are there any questions before we jump into an example? Any other questions? There were some really good questions, actually. Any other questions?
How do you adjust when you're, I've heard it, information gain. Like, how do you adjust when you hit your limit on what you're able to learn from the network? Or how have you found ways to adjust? So what you're gaining from adding additional nodes or changing your weights, you're stopping to learn. What do you, yeah.
I don't know. I think if I understand that correctly, is how do you determine the network architecture, like the number of hidden layers and a number of hidden neurons and inputs and outputs to be able to accurately make a prediction about the data? I think that's what the question is. And really, I think it is a lot of trial and error. As you start out small, you begin to train the data and see how close you were. You begin to see that the error was not close or that you're really not making a prediction. And I think once we jump into an example, you're going to see how that actually takes it's manifested. When we see this, you're going to say, oh, that we need to add more nodes because we're not getting enough clarity in making a prediction. And I'm going to explain that in a little bit. But really, to be honest, I think it's a lot of trial and error and starting out small with as few nodes as possible. Obviously, the greater number of nodes you have, the more complexity that it takes the training. And so you want to have the smallest amount of nodes as possible and still be able to accurately make your predictions, right? And that's really the key here. Label and formulation of the cost supervisor. I don't know enough about, there was a question about whether or not you can use unsupervised learning for neural networks. I have not gone through or read any papers or enough papers to be able to answer that particular question, because in my understanding, most of the time, you're going to use supervised learning to begin to train a network the way I just described. And there are other ways to adjust the weights and biases other than just gradient descent and using different things than backpropagation. But they all still use supervised learning, in that they're still using a training set where you know what the inputs and the expected outputs are. I have not really done enough research to know how a neural network would be trained using unsupervised learning, where you don't know what the output is and you're just assuming the network is supposed to learn and know what is right on its own. So sorry, that didn't probably answer exactly, but I would say you probably you and I both need to do some more research.
Yeah, I mean, when it comes to what we'll be getting into with the Grasshopper tools, we won't be covering them explicitly, but the Gaussian mixture and k-means clustering are probably good examples of unsupervised learning, insofar as you're feeding it data and then the algorithm's kind of looking for patterns on how to group things and cluster things together, and you're not explicitly feeding it a training set, right? So yeah, I also have not seen a neural network on an unsupervised implemented.
I'm sure there are people who are trying to look at it, but I have not tried to implement it or haven't researched that domain very well. All right, so because we're already an hour in, I'd like to try to go through a very simple example, which hopefully you guys got the example zip file that Nate sent out this morning. The one I'm going to open up is under example 0.1, and it's just the point sampling prediction. But in this case, I'm using the started one. There is one that's just without the word start at the end, and that's the finished version if you want to just look at that and see what we're doing. But in this case, the started one.
One quick bit of, I guess, housekeeping here. I'm going to paste in the chat 2 links in case you didn't get my email. One for these examples, and then one to also the latest version of LunchBoxML. So in case you didn't get those before, they'll be in the chat here shortly as Andy continues his demonstration.
Perfect. Okay. So this starter definition is very simple. All we're doing is creating a three-dimensional point grid. This is just a C# node. You're welcome to go in and edit it as you see fit. But you can see the parameters that you have available. This basically controls the resolution of the spacing of the point grid. That also begins to tell you how many iterations are in your training set, right? So if we increase this value, the output of this value, which is going to be what we're going to train the data on, is essentially the X and Y coordinates are going to be the training input, and the Z coordinate is going to be the output, right? So we're going to say, if you were given a value of 0, 0, or in this case, -1, our X domain is from -1 to +1. So if we were given this value of -1, -1 in the X and Y axis, what would the Z coordinate be, right? And so we have an equation, we can write an equation to make this surface. But what we're going to try to do is train a neural network to make a prediction to see if they can accurately predict what that z coordinate should be based on an x and y value. So the iteration here is going to control the density of this grid, but also the density of the training set. I'm going to just set it to 40 just to keep it quite low, but you can play around with that number. The x and y offset are simply adjusting the frequency or the pattern. Again, same thing with the frequency and amplitude and the pattern. The pattern you can play around with. All that does is change the shape of the point grid into different domains. But for now, for this particular example, I'm just going to keep it to a value of 1. So we're going to use this sort of sine surface, if you will. And also what I've done here is shown that the input range is going from -1 to +1. So in the x and y axis, we're going from -1 to +1. The output range is going from 0 to 1. So it's going from basically the origin in the z-axis to a positive value of 1. And that's important because remember, it's going to be important to determine which type of activation function you're going to be using because they all have different domains in which they work. So under LunchBox, there's a machine learning tab. And underneath that, there's something called the neural network trainer. There's also a neural network tester, which we'll use in a minute. But for now, we're going to train our neural network. So we can add that onto our canvas. And immediately, it's asking for what are the inputs and what are the outputs. So these have been set up as a data tree structure where the first data path contains 2 values. Those are our x and y. And then on the same path, but in a different tree structure output is our z value. So we're going to pass that as our input, and the training output goes into the output. And now what we can see is it automatically tried to calculate something, and that's because all these other parameters have a value assigned to them. You'll notice that it has something called a neural network output, and that's passing the neural network out so you can pass it into the other component that I spoke about, which is the neural network tester. And then we also have something called the error. And this is that error rate that I was talking about, where it starts off and the mean squared error for the first iteration through the training was 0.5. But as we go through, you can see it's getting much smaller. So as we train the data, those weights and biases are random. But as we train it on the data, it begins to get closer and closer to 0. And if we use a quick graph component, you can actually map that and see what that error output looks like. So we can assign different values to some of these different, or look at some of the values here. The first one is going to be the hidden neurons. Now, for starters, I would suggest that for this particular example, we're just going to keep the hidden layers to 1. So we're just going to have a single hidden layer, but inside that hidden layer, we can have a whole bunch of different neurons. In this case, let's set it to be something like 30, but we'll set the value in this case to 6. So I'm just going to assign that to the hidden neurons. You can see when I do that, it goes and makes this calculation. So we have a value here. And we also have assigned a learning algorithm. In this case, this is the learning algorithm that it's using to go back through and train the data. And as I mentioned, there's lots of different ways you can do it. The 2 most common ways are called, the most common way is called back propagation. There's another one called resilient back propagation. And the default is that resilient back propagation. It's number 1. But you can choose either back propagation or resilient back propagation, and it should be fine. The only difference really is that the back propagation one exposes that learning rate value as well as a momentum value that you're allowed to play around with and see if it adjusts the network parameters. But let's just leave it as this, and then let's see if we can actually test how well our data performs. So we're going to go back to LunchBox and go to the neural network testing now. So this one, we need to pass it in the network we want to test against. So that's going to be the neural network that we just created. We're now going to test it with some new input data and see what comes out. So now we have to generate our own input data in order to create this. So I'm going to just do something really quickly because we're a little bit short on time. I'm going to open up and just copy paste from the other one so that we don't end up wasting so much time creating certain examples that are easy to do, blah, blah, blah. This is calculating. Should just take a second. Maybe that was a bad example. Maybe that was a bad thing to do. All I'm trying to do is copy and paste the section. Come on. Maybe Zoom is causing it to, there we go. Is this section, which is a section to generate the training or the testing data. So if I look at this data, and I'm just going to change this back to -1 to 1, is what's happening here is that we have a random generator. In this case, it's a random generator, and it's randomly generating 20,000 values between -1 and +1. This is going to be my x-axis, and this is going to be my y-axis. And I'm changing the seed so that it doesn't come up with the same number every time. I'm then grafting it, merging them together, and then simplifying the tree so that the input values should look very similar to the input values that I fed it in here, right? Which is a path with 2 values on it, a path with 2 values on it, and those should be between -1 and 1. But that's the same thing I've got here, where I've got a path with 2 values, a path with 2 values. So that's going to be our values that we're going to feed in as our input. And the output is going to be the Z value, right? Is the predicted Z value, because we've taken our neural network, we've trained it, and now we're trying to test what this is going to be our Z value. So if we wanted to create a new point grid based on this data, all we have to do is, let's see, construct point here. And we know that this is going to be our X value. This is going to be our Y value. So it will feed that into X and this into Y. And let's see, is this, yeah, let's grab it. And this into Z. And so you can see we've created our grid. What I'm going to do is to move this over by going in and adding an expression and saying X + 3, just so that we can move this over some amount so that we can see our training data, and this is the testing data. So we have our points now, and I'm just going to copy and paste this section here over, and this is just the same thing, which is going to colorize our data. In this case, we just need to pass and then turn this off. So we're colorizing the data now so that based on the Z height, right? And what you can see is that we didn't do a very good job, right, at making a prediction. We tried to use our training data and our training output data, but when we fed it new data between -1 and +1, we ended up with something that looks like this, right? So we didn't quite do what we were looking for. And the first thing we want to do is try to change the neurons. So if I change the neurons to something higher, we should start to approximate. So now I've got 12 neurons, and you can see it's still only taking 1.5 seconds to train. Now you can also improve your accuracy by, the iterations are by default set to be 500. So you could increase the iterations. You could also increase this. If you can see, it's not quite the same pattern. If you increase this to be higher, you'll start to get more clarity as to, how many. But again, you want to try to determine what is the minimum amount of nodes and network complexity to achieve what it is you're trying to achieve. And now you can see we're getting pretty close. Again, I think if you were to take a value here, and let's say this is the number of iterations, and we say 2,000 instead of 500, we should be able to get a much closer value to 0. You can see we're already at 0.01. If we make our iterations be 2,000, now it's taking 7.3 seconds, but our output is 0.002. And so we're getting a much closer approximation because we're training the data for a longer period of time. I'm going to go back to 500 just to keep it fast. Now, another thing we might want to look at is the activation function, which I talked about. If I were to right-click on the activation function, you can see that I have a bipolar sigmoid, which should also work. The problem is a bipolar sigmoid is going from -1 to +1. And let's see if we can, this might just be a factor of the network architecture. Not, there we go. So you're still getting a close approximation even with a bipolar sigmoid and 500 iterations, or 1,000 iterations, but you're not getting the same resolution because your output range is 0 to 1, and your bipolar activation function is going from -1 to +1. So you really wouldn't want to choose a bipolar sigmoid function in this case because it doesn't give you the full range of your output, if that makes sense. So in this case, I would choose a sigmoid because the Z values are consistently going somewhere between 0 and +1. But that's not to say you couldn't try to see what a rectified linear equation activation function would look like. And let's look at what happens to the data. So here, a rectified linear, again, we're trying to fit a linear line to our data set. And so it tries to use linear equations to, or a linear activation function to make that approximation. And so the output that we get is no longer a smooth transition, but it follows along this linear line. So I think this is a fun example to look at in explaining how the different activation functions work. Not all of them will work. Like if we try a threshold function, it probably will fail. See, this doesn't work because it's basically a stepwise going between 0 and +1 and doesn't really know how to approximate the type of data that we've given it. But in this case, I think a sigmoid is probably the activation function we want to use. And we can really begin to play with either the learning algorithm, so we could try to play with backpropagation instead of resilient backpropagation. So you can see I get a different result that's fairly accurate using that. It also gives me 2 more parameters to play with, which is the learning rate and the momentum. Remember, if you remember, the learning rate is the step through the process each time, how much you're multiplying to get that value. And so you can play around with some of these different parameters and see how those begin to affect the prediction. Now, one thing what I talked about overfitting is the fact that we've given it data that it has already seen before, right? We train a neural network and we can get a very accurate prediction, in this case, less than 1,000th of a value. We're very close to approximating 0. And if you increase the iterations and things like that, you can almost approach 0. So you can almost make a very, very accurate prediction as to what that value might be. But the real question is whether or not, how does it perform when it's given data it hasn't seen? So if we were to try to do, let's say, -2 to +2, right? Now we're giving it new values it hasn't seen. And you can see that we're picking up certain things. The frequency of the yellow is being picked up, but we're really not picking up the frequency of the green or the lower domain in our function, as well as the patterning of the sign. And so again, if you begin to play around with some of these different algorithms, in this case, I'm using the learning algorithm. Instead of using backpropagation, I'm using something called the Levenberg-Marquardt learning algorithm. And you can see it doesn't do a great job either. But it is picking up, the periodicity of these red circles. It is starting to pick up on that periodicity. And if you make certain changes in your network, you might begin to approach a condition that can closely, but not, I still haven't, even in this data set, been able to generate a set that is very good. Here you can see it's probably about as close as I've gotten to making predictions, even in data that it has never seen before, making predictions about what should happen based on the patterns that it's been trained on. So that's what we talk about when we talk about overfitting a model. is how well does your model perform on data that it has never seen before? And that's what we talk about when we talk about overfitting a model. And there are tests, I mean, this in particular is how well can you begin to look at the data and give it new data it hasn't seen, and how does it perform? Are there any questions? Because I have one more set of slides I'd like to show, but are there any questions about any of the stuff I just showed? All right, hearing none. I'm just going to switch back over to PowerPoint before we, I think I'm already here. So before I close and hand it back off over to Nate, and he performs some magic of his own, really what I wanted to do was show one real world scenario where you might use something like a neural network. And I mentioned that I did my dissertation on thermal comfort predictions for office spaces, particularly using a neural network to optimize personal comfort. If we think about what indoor comfort means, especially in relation to an office space, it's the collective whole of all of the physical properties which begin to affect someone's heat loss and or respiration. There was a study done in 2012 by the Center for the Built Environment, I think of over 34,000 occupants, on what are the factors that most affect occupant satisfaction. And what was found among all of these is that, as you can imagine, temperature and sound privacy are two of the most glaring factors that affect personal satisfaction in an office space. And we can see this every day when you walk through an office environment. Some of you might be, well, we're not walking around office environments as much anymore, are we, with COVID? But you might even see this in your own home, where you might have a desk fan on your desk and a portable heater below your desk and some headphones and some shades that may or may not work. And all of these things echo to the fact that oftentimes we have very little control over our environment, particularly in an office setting. And so how can we begin to create an environment that alleviates that? And I think part of it is the way we regulate buildings. If we look at the standard for regulating a building, it's regulated by a code called the ASHRAE Standard 55, which essentially tries to describe what are the parameters that the environmental and personal factors which will create, let's say, an acceptable environment for the majority of occupants. And they specifically define a majority as 80%, which, if you think about that, in my opinion, is pretty wrong, because that means 20%, they're already admitting that 20% of occupant satisfaction can be dissatisfied with their office environment, and it's still okay. And if you think about how much 20% of the entire office workforce, you're talking about millions of people who would be dissatisfied going to work every day just because it's either too hot or too cold. But the way the ASHRAE standard works is they use something called the predicted mean vote. And this was a model that was developed in the 80s by a guy named Ole Fanger, which essentially did a whole bunch of studies on people where they had them rate on a 7-point scale whether they were hot or cold, where a value of +3 would be hot, a value of -3 would be cold, and really the sweet spot is 0. And what they found is that there were essentially 6 different factors that affect thermal comfort. The first being air temperature, which makes sense. Mean radiant temperature, which is the temperature that is radiating off the surfaces around you. Airspeed, makes sense, is how, if you're in a windy space or in not a windy space, obviously that has a factor of how hot or cold you are. The relative humidity in the space. And then there's 2 personal factors which can really drastically affect someone's comfort, which is how much clothing are they wearing, and the metabolic rate, how much work are they doing? So if you're digging a ditch versus sitting in a chair, that obviously has a very different impact on how hot or cold you might be. And so this is the actual equations that he developed to make a prediction for this predicted mean vote. And I'm not going to get into this, but essentially you can imagine this is one really long nonlinear function. And we just talked about how neural networks are really good at approximating nonlinear functions. So it was a really good choice to choose a neural network to make a prediction about how to make these predictions. And once you know the predicted mean vote, so the value between -3 and +3, you can feed it into this graph, this other equation, which will tell you essentially the percentage of people who would be dissatisfied in that space, right? And another thing to highlight here, which I think is a little bit odd or off, is that you're never going to get 100% satisfaction. Even at its best scenario, 5% of people will always be dissatisfied in your office, which can either be seen comically or not. So I developed a training algorithm, a training interface for developing a neural network. And so this was the left-hand side of this interface really shows you that how, in this particular scenario, it's using that nonlinear set of equations that I just showed that were developed by Mr. Finger, where we have those 6 values that we know, which are the air temperature, the radiant temperature, the airspeed, humidity, the metabolic rate, and clothing. And we can change those values and see what the change in the predicted mean vote would be. So you kind of get an intuitive sense based on changing these values, what the predicted mean vote would, how that would change according to that function. We can then go down here and create a training data set. In this case, it's randomly going to generate a bunch of data. In this case, inputs and outputs. Let me go back to that histogram. It's going to randomly generate those 6 input values and run it through the equation and tell us what the predicted mean vote would be. And that's going to be our output. So we have 6 inputs and a single output, which is the predicted mean vote. And so this is the histogram of those values, which essentially tell you what the output would be, the predicted mean vote. We can then load that training data that was just generated into the middle section, which in this case allows us to set up the architecture of the neural network. It allows you to control the number of nodes in your hidden layers, which type of learning algorithm you want to use, and activation function. And then you can begin to train your algorithm. And here you can see the mean square error. As it learns, that error rate as it learns through each iteration is going to get closer and closer to 0, right? And that's what we just talked about as the cost function, this mean square error. What the difference between what we expected and what we computed should get closer and closer to 0 as it learns how to predict your function. Now that we've trained our neural network, we can then load it into this side, and now we can adjust these sliders, and now it's not using the set of equations, but it's using the neural network to make the predicted mean vote calculation. So the output should be the predicted mean vote. And what we can do is run the current settings, which is to say, take that same training data and rerun it through the network instead of this time using the network to make the calculation. And if we have a very good model, the light blue and the red should match very closely, right? So that means that the model is fitting the data quite well. But here's where I think the real power of neural networks comes, is in its adaptivity. And what I mean by that is, let's say we had our current set, so this is the ASHRAE standard model. Let's say we went back and said, under these certain conditions, it thought I was neutral, but in reality, I'm quite cold. I can then go back and say, take that value and propagate this feedback through the network and readjust the weights so that based on this new data, based on this new evidence. And when we do that, it will create a new profile. So you can see I can run the settings, and now you can see the model has shifted. And that, to me, the power of neural networks is that we have the ability to, in this particular instance, we created a model that was sort of the universal standard of what we think people should feel in space. But now, once we give it personal feedback, we can begin to create our own profile, right? Our own profile that is either cold shifted or warm shifted in order to match our own personal preferences. And when you couple that with an online interface that I developed, which allows you to scrutinize sensor information that was being calculated. So this was also some hardware that I developed, as well as other types of hardware like this fan that I developed, which uses facial recognition to direct cool air towards parts of the body which most affect comfort, like your face and neck. We can then show that with neural networks, we can save on energy consumption, we can improve overall user satisfaction, and we can decrease the overall desire for more control. And so this was a very quick recap of my dissertation study, but I think it begins to show you, you know, the power of a neural network and how it can be used in a real world scenario. Are there any questions? I think we're right at about the 90-minute mark, and that's where Nate and I had sort of thought we would hand off. Are there any questions? I think, well, first, are there any questions that I might be able to answer? How to remove and how to find and remove outlier in training data. So there was a question about how someone would go about finding and removing an outlier in training data. And honestly, that's more of a statistics question than it is a neural network question, right? So there's a number of different algorithms you could do. You could loop through the data and look for, you know, the Gaussian of it and begin to highlight ones that are outside a certain range, you know, the 25 to 85, 25 to 75% range. You could also, I mean, there are a number of different statistical ways you might go about that. Nate, do you have any off the cuff thoughts about how you could go through a data set and remove outliers?
Yeah, to me, that's like you said, that's almost a question of curation. You know, in advance of providing it as training data. Like you could implement various methods, as you said, where it's like, you know, if you're able to view the data in some way and look to identify stuff that's outliers, maybe that's actually an interesting kind of way to look at some of the unsupervised techniques, like clustering as an example, to kind of prepare the data to kind of understand, hey, there's groupings of data that exist right in through here that seem like it could belong to each other. Then you have these outliers that are sitting out kind of in some other space. And you use that as a way to say, okay, well, I'm identifying these outliers and maybe my intent is to eliminate them. So I'm going to cull them out and then I'm going to feed in the data set. So I think there's different ways to, mix and match statistical concepts and maybe even other learning algorithms to do that.
Any other questions? If not, Nate, do you still want to take a short break, or do you want to?
Yeah,
continue?
so I mean, we've been going at it for about 90 minutes. I think I don't know if there was an intended break baked into the workshop scenario, but I would suggest that maybe we take 5 minutes, let people get refills on their coffee and or water, and we reconvene maybe at 2:43 Eastern time, and we'll pick up with Semantic and some further kind of examples of using the neural networks with some predictive capability.
Great. And I'm going to stop sharing because I think at this stage, Nate is going to run through some grasshopper examples. So he'll be able to share his screen.
Great. Cool. All right.
Thank you.
5 minutes.
Sounds good.
Okay. It's been about 5 minutes. And it is 2:43 Eastern, 1:43 Central. So I think we can pick it back up again and get into some expanded topics and adjacent topics, I think, as it relates to the uses of machine learning and the potential for its use in the overall design workflow. One of the things that occurs to me as I listen to Andy talk about neural networks, and the structure and shape of data, is that the successful implementation of a machine learning concept hinges, especially supervised machine learning concepts, hinges on our ability to structure and curate data. And there are many aspects of our design process today that leverage data in different ways. And And I would say that if I were to take a step back and look at the building design and construction industry and characterize the data that we have at our disposal, I would perhaps say that it is messy, uneven, oftentimes incomplete, and it varies from design stage to design stage. So it may be more common to have more well-structured data, say, at the end of construction documents than you would have at the beginning of a given design concept or schematic design stage. So I would say that there is a lot of data about buildings and the design and construction and operations process, but it's sometimes hard to figure out how we're going to curate and make use of it. We've been developing various tools that focus on different aspects of data curation and management, with the kind of desired outcome of using data to equip different processes like what Andy was describing with neural networks. One such tool that we're going to talk about a little bit in this session is Semantic. And we're going to use the Semantic plugin for Rhino that we've published as a way to curate and integrate data within the Rhino modeling context. So if I were to look at an interface like Revit, right? Revit itself has a way to manage properties on objects. If I were to draw a wall in Revit, as an example, this wall has properties and data assigned to it. We know what type of wall it is. We know its length. We're able to build and design schedules off of this object. And Revit kind of, basically as a building information modeling framework, you have this ability to query attributes off an object, and it makes it very powerful, I would say, as an information management tool. However, this is not necessarily the tool that you're going to be using in early design, because sometimes highly structured information and the way that tools like this are used in a parametric kind of way can be kind of inflexible in some contexts when you're trying to iterate and understand a set of design problems. So we often see that folks rely on tools like Rhino as a highly flexible, free-form geometric modeling engine. And unless you start to get into Grasshopper or scripting on top of Rhino, the ability to control attributes and manage them in different ways is in some ways out of reach. So we created Semantic as a way to bridge the ability for a Rhino user to assign data points to their objects in a flexible way and track them as the design develops. So I'm going to first introduce Semantic and its interface and kind of use it as a way to kind of classify objects and assign data points to objects. And then what we're going to do is we're going to get into the ability to leverage information that exists inside of the context of Rhino to train a neural network, and then use the neural network as a design assistant to classify unlabeled or unclassified information. So it'll be a neural network as used as in some ways, a classifier type of context. And hopefully this provides an interesting dialogue on how a neural network can really be an assistant to extend a designer's ability to manage complex data and quickly automate certain processes in the ability to kind of assign data points to objects. So what I'm going to do is inside of Rhino, I'm going to make a set of surfaces. And I encourage you all to do the same. I'm just going to make a set of planar surfaces. They're going to kind of be representative of floor objects, if you will, kind of stacked set of surfaces in Rhino. And I'm going to just use the rectangular surface tool to do this. So you can see that I've got a shaded surface object there. I'm going to jump into my elevation view, and I'm going to copy that up a few times, not too many times, but maybe I'll do like 10-foot increments. So we have a couple of surfaces on our screen, and maybe I'll stop at about 5 surfaces. And I'm just, for the purposes of this, I'm going to just kind of stretch them out a little bit, make them a little bit bigger, more kind of proportionally looking like a set of stacked floors, if you will. So we understand these, that we might, as we look at this, we might say like, oh, okay, this is starting to indicate some kind of building structure where we have stacked floor plates in 3 dimensions, each of these representing a level of a building. There's nothing in Rhino telling us that these are floors. There's also nothing at the moment telling us inside of Rhino what the various attributes associated with these objects are. We don't know its area. We don't, unless we query the area command, we don't know what its area is. And we may want to have other things associated with this, such as like cost information, cost per square area, and so on. And so this is where Semantic comes in. Semantic is a interface. If we are in Rhino with Semantic installed, we're able to run the Semantic panel command. And what this is going to do is it's going to activate a dockable window that can sit alongside your other Rhino windows, much like the properties window, the layer window, or other attributes that may be assigned to it. And it basically becomes a way to implement object properties and manage user data that can sometimes exist on objects. So here you can see that there's currently nothing there in the object properties. If I click on any one of these objects, it's not conveying any particular property set or anything like that. But what we're going to do is we're going to use Semantic to design a set of properties on top of this. So the way that we can start to build in properties with Semantic is to use what's called the property group manager. And you'll see at the bottom of the Semantic interface, there's a checkbox that we can activate the property group manager. And it's going to set us up with this, basically a listing of available property groups. So we can establish object level properties, i.e. properties that are going to perhaps indicate some specific set of attributes for a given object. We can also establish document level properties, and those are kind of more global parameters. It may convey some kind of project information. It may be a contingency multiplier if you're building up some costing, and so on. The internal properties. These were conceptualized as ways of communicating common attributes about an object, such as its area or linear length. One of the things, this seems like such a simple thing with respect to what Andy just covered with the complexity of neural networks. To this day, as consultants, we still see architects and planners using area commands in conjunction with their calculators to get a sense of how much building area they have in kind of a very manual way. So at a minimum, we were like, well, can we create a mechanism for just simply reporting some area properties as part of this interface? So what I've done here is I've selected my objects and I've said, okay, I'm going to assign these to the internal properties. And what this is then giving us is now these objects are assigned to a set of properties that are reporting the area of the object. And if this were a curve, it would be providing the length, for example. And then multiple select is giving us the summation of the areas of the objects that are selected. So it becomes this kind of way of quick reporting of some of those attributes. But I can also then define some custom properties. Like what if I wanted to understand area by department or area by some kind of grouping parameter? What I would then do is say, okay, well, I'm going to add a new property set here. So you can see that there's a plus sign. And what I'm going to do is I'm going to create a new property group. And I'm going to add an object level property group. So there's 2 types of property groups that we can add in here, right? One is something that exists at the object level, something that exists at the document level. So I'm going to go ahead and add a property group here. And I'm going to call this a programming planning property group. So these are going to be attributes on an object that may relate to the programming and planning operation of a given design scenario. And you can see that there's some applicable Rhino object types. So BREPs are also surfaces. So if I wanted these groups to apply to BREPs in my Rhino model, or my set of curves in the model, points or meshes, Those are checked by default. But in this case, I want my property group to only apply to my surfaces. So I'm just going to have those checked to be rep. I'm then going to add a new property into this property group. So properties inside of the semantic world are much like any other object type or kind of property type in other environments. You have a couple of options. There's the idea of assigning some text properties. So if, manually written or typed out strings can be assigned. We have numeric properties, so numbers, integers, things like that. We also have some categorical operations, where if we wanted to create a fixed drop-down list of selectable items, we can do that. We can also have Boolean on and off parameters, and also some date-time parameters. So we've kind of used this as a tool to set up conceptual costing models and other things. In this case, I'm going to first add in a number parameter. And this is where I can start to define a property. So a property, in this case, may be cost per square foot. So I'm typing in cost space SF. That's going to be the name of the property. We don't need to worry about grouping fields at this point. We also have default value. If we wanted to provide a default value, in this case, I'm not going to. I'm going to simply, actually, you know what? I am going to provide one. I'm going to provide one at 150. And the number format allows us to describe how we want this thing to look, essentially, in the interface. At the underlying level, this is a number, but we may want it to display like a cost value. So I'm going to choose this number set here. So it's going to be formatted dollars and cents, and so on. If I wanted this exposed as a slider interface, I could. I'm not going to at this point. It's just going to be numeric entry field. I'm going to hit save. I'm now going to supply this with a categorical property. So we're now going to say, okay, we're going to have our cost property existing in this group. I'm also going to create a categorical property, which is a fixed selection of drop-down items that will be exposed. And you'll see what I mean here in a second. In this case, I'm going to simply call this department. All right, so we're saying that this is going to be a property that's going to have the name of department. And now I need to supply a list of what departments I want to have represented as selectable objects. So I'm going to say that I want this category to be office. I'm going to add this into the list. I'm going to create one that's going to be residential. I'm going to add that in as so. And maybe retail, for example. So I now have 3 possible categories to select from, and maybe I want to do something where I'm manipulating the color of these categories as well. So I'm going to, just kind of adjust the colors so they're kind of keyed in a little bit differently. Office being green, I'll make residential have more of an orange, and retail more of a maybe a violet or purple here. So they're all a little bit different. And so now these would basically inform a selection of objects. And I'm going to go ahead and hit save on this property editor. And now we have a programming and planning group that is containing cost per square foot and department. And I'm going to go ahead and hit save on this. And now I have a new property group available that I can say I want one of my objects to subscribe to or be assigned to. So I'm going to go ahead and select this grouping of 5 surfaces, and I'm going to assign these properties to those surfaces. So what this now means is that we have in Semantic, this interface, when I select an object, I'm able to adjust and assign a given cost per square foot. I'm also able to describe what this object is in terms of its categorical placement. So again, it's about providing these attributes on these objects that we may want to track over time. At this point, what I'm going to do is I'm simply going to close my property groups editor and just work with these 2 properties for a little bit. So we have this makeup of surfaces, and if I click through, they all have the same attributes. What I'm going to do is I'm going to go through and alter these attributes a little bit And so we can start to see how this starts to play out in the overall experience of Rhino. So this bottom surface in Rhino, what I'm going to do is I'm going to change this to a retail label. And I'm also going to change the cost per square foot to maybe 120. So it's different than the others. These next two surfaces I'm going to say are, we'll keep them as office, and maybe we'll bump these up to 180 cost per square foot. And then this top two surfaces I'm going to say are residential. And maybe I want to make this a budget of 160. So they're a bit different from each other. This hasn't changed the appearance of any of our Rhino objects. I can still stretch and pull these in different ways. If I scale them, we scale them, we can see that you know, my area report is changing, of course. We're getting varied properties assigned here. But maybe I want to see what these look like in terms of their departmental assignment. So what you'll see is that up at the top here in Semantic, there's a preview feature. Right now, everything's being colored by layer. I'm going to click on this drop-down and say color everything by department. So now that key of different departmental properties is becoming apparent in my visual display, and is overridden the colors of my objects to be, you know, to communicate this this selection of categories. Which can be very useful if you're kind of doing a kind of a planning and programming exercise, or trying to visualize objects by some of these departments. And you know, in some ways, this is like, you know, the basic flow of Semantic. You know, you're defining properties, you're establishing and editing values of properties, and you're to some degree visualizing them. In Semantic, we also have this ability to report values from our model that we're building up. And there's what's called a report manager at the base here. And reports in Semantic are like schedules. So if you, for example, were in Revit and you developed a room layout or a floor layout, you could schedule each object and have it report its area or other property inside of the Revit environment or building information environment. Semantic uses a very similar analog where you're building up a report of some set of attributes that are in your model. So what I'm going to do is add a new report, and it's going to activate what's called a report builder. And if you've ever used business intelligence software or used you know, Excel pivot tables, there are some analogous ways that we're able to build up things insofar as you have dimension fields that indicate summarization groupings for different attributes. And then you have measures, which are like your numeric expressions and so on. In this particular case, what I'm going to do is I'm going to build up a report that very simply communicates the total cost of a given department based on the area values that are on these surfaces and the departmental breakdown that we established. So we can take a look at how that starts to pan out. So I'm going to call this department report, and I'm going to establish as my dimension the department as my value. So this is going to mean that my dimension is going to be looking for the departmental values that are assigned to these various objects. And for the field name, I'm going to, you know, you can call it something different than department. In this case, I'm going to call it the same value as the property. So you can assign those to be the same value or something different. It's just a way that it's just what the column that our report's going to have is going to list it as. The measure field is going to be based on some kind of numeric expression that we're going to use. And in this case, what I want to use is the field name of, and we'll call this field, I'll call this total cost as an example. And it's going to ask us for an expression. And we do have a very, you know, a very simple way to create some kind of expression with these using the names of the properties that are on our objects, right? So I'm going to use cost per SF. You can kind of see I'm using an open bracket there. And I'm going to say, I type in the cost per SF parameter like so, and I'm going to multiply it by the area. So I'm taking this parameter here, cost per SF, which the object I have selected is 160. You can see that it's got an area value here. And what this is simply going to do is it's going to create that expression of cost times area. And then it's going to organize a table based on this department. So I'm going to hit save on this. And we now have a report that we can activate and deactivate as so. So I'm going to go ahead and click activate. And what this is doing is it's now created a report that I can use, that it's going to report out what's the total cost of office versus residential versus retail based on their area calculations and based on their cost per square foot. If I go back into, I'm going to go ahead and close this for right now because I want to do one more thing. We are talking about dollars and cents when it comes to the subject of cost. I forgot to add in that I wanted this to be formatted as dollars. So I'm going to also add that in and hit save. And then I'm going to activate that particular report again. So now we have that formatting taking place. And of course, if I go back in and it looks like there's dollars and cents, maybe I want to add in also this idea of commas. So those get formatted as well, activate that. And we have now some further formatting to that numeric output. This stuff is live. So if I start to stretch and push and pull these various surfaces around, you'll see that the computation of area times cost per square foot is changing. If I reassign some of these objects, maybe I want to make this second floor here retail, that report is also going to change and adjust as necessary. So again, Semantic is about this like assignment of data. And what we can also do with these reports are export them if we wanted to kick out a JSON file, a CSV file, or an Excel file of some of these reports over time. Becomes a way for us to do this type of activity. That's kind of the basics of Semantic. We're able to create properties, generate reports, and hopefully make that and export that data and report that data as we need to. We can also do a level of data automation with these tools. So I'm going to go ahead and close out of these objects, and I'm going to go ahead and go into Grasshopper. And Grasshopper is opening up on my other screen here. There we go. Any questions on Semantic so far? It's pretty straightforward when you compare it to gradient descent, I think. Okay, cool. If there are any questions, feel free to let me know. So inside of Grasshopper, what we're going to do is we're going to start to use Grasshopper to automate some aspect of this process. We can read data in from Semantic and the semantic data into Grasshopper. We can also assign values to our objects. So what I'm going to do is first I'm going to demonstrate how you might read data in. And what I'm going to do is do a very a typical workflow in Grasshopper to bring a geometry from a certain layer into the Grasshopper environment using the geometry pipeline tool. These objects all exist on the default layer, so I haven't changed their layer at all. So what I can do is just going to zoom in and do a default layer assignment. And I'm going to choose brep, which is then going to reference these objects from Rhino into the Grasshopper environment. Kind of see they all got this shade of red to them because we're seeing the overlapping of the geometry preview. And inside of, with Semantic installed, you're going to have a Proving Ground tab, and there's going to be a set of tools called Semantic V6. And what I want to do is I want to read the properties on these objects and pull them into the Grasshopper environment. So I'm going to go ahead and pull out the read properties. And what this component's going to be asking for is it's going to be asking for a set of GUIDs. These are going to be Rhino GUIDs that exist, that basically represent these objects that have some data on them. And we're also going to be asking about, so it's asking us about the fields to be pulling in. So I'll start with the GUIDs. Right now we're pulling in the geometry. We should have a listing of some referenced surfaces here, referenced BREPs. We can easily get the GUID, the unique identifier of these objects, by going to the Params tab in Grasshopper and pulling in the GUID parameter value. And this is a node that just has the icon ID. And what I can do is connect the pipeline in. And what that's going to do is it's going to report, instead of the reference BREP, it's going to report the unique kind of identifiers for my objects. It's an important, very important concept for how we're tracking the uniqueness of an element and then using these as lookups to then access the data that each unique element contains, right? So I can pass this GUID in to the input for GUIDs, and then I need to identify the field that I want to pull in. So under Proving Ground, Semantic, I need to identify a property field. So there's a component object for this, where we have the name of the field, some filter as we might seem fit. In this case, we're going to grab all of them, and then a target, whether or not it's a class, group, or property. I very rarely use these in some scenarios. I mostly just reference things by the name of the property. So what I'm going to do is, going back here, you can see that we have a couple of properties that we can access: cost per square foot and also department. Maybe I want to bring in the department parameter or property into our Grasshopper environment. So what I'm going to do is pull out a panel, and I'm just simply going to type in department. Zoom out a little bit here so I can resize this, pass this in there, like so. And I'm going to pass this department field in there. So what we're now getting is we're supplying it the list of objects, we're supplying it this department field. If I hover over our objects here, we can start to see that we're getting we're getting some replicated information. So we're getting a tree of GUIDs. We're also getting our geometry, so those are aligned. We're then getting our property, so the property name as a list, but then we're also getting our value of these properties also being referenced into the Grasshopper environment. So this becomes a way for us to reference this information. Another thing that's important about this is the kind of the possibility for some real-time feedback. And by default, this particular node is set to be Rhino silenced. So what that means is that because of with anything where you're live reporting stuff out of Rhino, and as you'll see, pushing stuff back into Rhino, there's these opportunities to create some pretty unhealthy continuous loops of information if you're not careful. So this is by default set to Rhino silenced. What that means is if I start to stretch some of this information or change up the information from the Semantic tab, this information won't update unless I actually refresh my Grasshopper definition. If I want this to be kind of more live and dynamic, I can uncheck Rhino silenced, which is now listening for changes inside of the Grasshopper environment, to where if I change this to office, we'll see that that property value for that particular object has changed and is now listening and reporting out its value in the context of Grasshopper as well. So we've got kind of a live loop happening with Grasshopper, which kind of makes an opportunity for, if you really wanted to get into using Semantic as in some ways some kind of remote control panel for Grasshopper, where a change on a semantic property dovetails into another definition, makes that quite feasible as an idea. So this is reading properties as one concept. We can also bring in our schedule or our report if we wanted to as a set of things that are referenced in. And so what I'm going to do is I'm going to find in my dropdown for Semantic and Grasshopper, you'll see that there is a Semantic report node. And what the Semantic report node does is it looks for the available reports that are in Semantic. In this case, we only have one. And I'm going to go ahead and select it. And what it's going to do is it's going to auto-generate a node that represents that particular report. So you can see that we have department and total cost listed. It's also bringing in the geometry of that report and the associated GUIDs. So this then lets us start to reference the schedule. So there's all the total costs by the various departments that we have being pulled in. So this node is generated on the fly, and depending on the number of parameters that you've referenced in your report, this could grow. Another useful thing is that it is reporting the associated geometries that are being referenced in by these objects, as well as the GUIDs. So I wanted to kind of highlight this because it starts to now set the stage for a particular exercise I wanted to explore with you all related to neural networks and how we might begin to use data-rich objects that are coming in from Rhino, train up a neural network, and then use that neural network to make predictions on other geometries that may exist inside of Rhino. Any questions about this overall before I get into the main example? This was all really context. Okay, I'll keep moving along then. What I'll do is I'm going to jump into another example. This is an example that came with the data set that we provided. And the intent of this example is we have a set of surfaces that represent layouts for a set of office spaces. And then we have some of these objects in the model are classified. So they have attributes assigned to them. Here you can see different colors representing different space types. I'm going to go ahead within this particular test office block model in the data set provided. I'm going to activate Semantic. And what this is going to do is it's going to give me my Semantic panel. I'm going to go ahead and dock it alongside my other pieces. And I'm going to go ahead and click on one of my objects here. And what we're going to see is something not so dissimilar to what I had built up from scratch in the other file. You're going to see that I have what's called a suite type. And the suite type has some categories: small, medium, large, unclassified, and conference center. We have the cost per square foot parameter that I created before. I also have a couple of empty parameters that are all set to 0 right now, which refer to desk count. And the desk count has two scenarios. One is a standard desk count, and then one is another desk count that may be related to social distancing and things that we're experiencing right now globally and in the world that are going to affect how we start to design spaces and account for them. So what I'm going to do is go through a scenario where we're going to use this data. You can see that we've got a series of what I'm calling just a handful of spaces here. We have project A, which has a number of classifications according to determining whether something's a medium-sized office or a small office. This is another project, again, speculative, that starts to suggest that there are these larger offices, and there are variations. Each of these has slight variations in size. You can see that the dimensions of each of these objects is slightly different, and then it's getting a classification. And then we're also looking at project C here, which then introduces kind of this idea of some very large spaces that may be conference room oriented as a basic file setup, and again using semantic parameters that are embedded into them. We then have this what I'm calling a project prediction off to the side. This is, if I click on it, a set of unclassified surfaces that have no cost associated with them. And the makeup of this particular model is different than the makeup of some of these models. Like the dimensions are, might roughly fall into the same range of size as some of these objects here, and so on. But everything's unclassified. So I could either make a decision to say, okay, well now that I've roughed out a set of spaces, I'm going to go through and manually tell these spaces what they are. So I'm like, okay, this one looks like a medium conference room. This one here looks like it's a large one, and I might want to do this manually. It's kind of how we work in Revit right now, right? Where we are classifying. When we place a room, we have to give it a name or select from a list. It all becomes very kind of manual and quite frankly tedious, especially if you're designing large amounts of space and having to classify and give them different attributes. So what I'm going to do instead is I'm going to train a neural network to understand some dimensional characteristics about these pre-assigned buildings and their classifications. I'm going to train the network on this data such that it will predict and apply a set of classification attributes to this unlabeled set of data. And we're going to kind of explore in some ways how Andy went through that set of points to understand a geometric function. Instead, we're going to kind of derive a neural network that can understand the shape of the data as it pertains to classifying a space in an architectural sense. So I'm going to go ahead and activate Grasshopper. And what we're going to do is open up a document test, a sample file here called suite type classifier start. This is also provided inside of the sample data that we've given you, the training data set. I'm going to go ahead and open this up. And you're going to see that there's going to be some similarities between this particular definition in terms of its overall structure as to what Andy built up. Insofar as we're going to first need to train some data based on existing information, existing labeled data. We're then going to use that neural network to make a prediction on this part of the graph. So first thing I'm going to do is I'm going to reference some surfaces out of the Rhino environment here. You can see that we've got a node for doing this already set up. It's called input surfaces. I'm going to go ahead and right click, and I'm going to choose set multiple VREPs. And I am simply going to select maybe project B here. I'm only going to select a subset of all of these. You, of course, can choose any subset that you want. And I'm just going to choose one of these projects and hit enter. And this is going to bring them in to the Grasshopper environment. And you can see what we're doing with this set of surfaces is we're deriving a few things in Grasshopper from this reference. The first set of things that we're doing is we're getting some geometric information about the object. We're measuring the length and width of all of these blocks as they exist in the Rhino environment. And we can see that under our test data here, we've got the length and width being prescribed or kind of analyzed. So these are the length of every rectangle. This is the width of every rectangle, and so on. We're then also bringing in the semantic properties for what the suite type is in this example set. So it's taking the reference data, and it's also then giving us the fact of, is it a small suite, a medium suite, a large suite, or is it a conference suite, and so on. So this starts to then set up the opportunity to derive a network that can learn this. So what we're trying to do is say, okay, for every dimensional characteristic, let's use the dimensions as an input, and then as an output to the network, let's give it some kind of classification, whether it's small, medium, large, conference, or so on. And we could envision a scenario where I'm using dimensions, length and width. But maybe there's potential to expand this to adjacency or distance from different services, other kind of spatial attributes to make this kind of a smarter scenario. But to keep things simple, we're using these as 2 inputs and 1 output. The other thing that's kind of important to note in this scenario is that I'm pulling out the text-based property, small, medium, those types of categories that are on our objects here, right? But for the neural network, we need to get these into some sort of numeric format. So that's one of what the C# algorithm is doing. If I click into the C# component that we have here, you can see that it's taking the various categories that are represented by text and giving them a set of values between -1 and 1. So small object 0.75, medium 0.25, or -0.25, 0.25, and 0.75. So it's kind of like taking that range and sticking on to them determining what a large one where it should fall numerically within a given kind of domain, right? Which then gives us inputs and outputs here. So here's our dimensional characteristics, and then here is our desired output. So now we can start to pick up where Andy left off and start to build up a neural network from this to predict spatial classification. So what I'm going to do is I'm going to go to the Proving Ground, LunchBox tab, and we're going to go through a set of scenarios here where we start to configure the neural network to learn this data set and make some predictions. So we need to first build up a trainer. So here is our trainer with the default set. You can see it's requiring inputs and outputs. And I'm going to go ahead and pass in my inputs, which are going to be my dimensional characteristics for every surface, and then my outputs being the numerically translated classifications, like so. And since it's already has all the defaults set, we can see that the network has completed, and maybe I want to now kind of have a look at what these settings are. So we have 1 hidden layer. In that hidden layer, we have 6 neurons. We're using a resilient backpropagation learning algorithm. Our activation function is sigmoid. Alpha is 2, and iterations are 500. Right off the bat, the first thing I want to change when it comes to the activation function is go from sigmoid to a bipolar sigmoid. And the reason for that is an understanding of the range of values that I'm working with here. As Andy said, like if you think about the sigmoid activation function, you're looking at values that are normalized between 0 and 1, bipolar sigmoid -1 to 1. And if I start to look at, for example, these outputs, we have values going from -0.75 to 0.75. So these are being constrained into that domain. So I'm going to change my activation function in this case to be bipolar sigmoid as my first change. I also want to do some adjustments to some of these, or at least provide inputs where I can quickly adjust my hidden layers and my hidden neurons as an example. So I'm going to use a panel here to say, maybe beef up my number of hidden neurons to 16, put those into the hidden neurons input. And then maybe I want to create a couple of, or have the control here exposed to control how many hidden layers I'm working with. I'm going to keep it at 1 for now, but I want to just kind of expose that as an input. So we have an output here. We have our neural network. We also have our error rate that we can look at, and as Andy indicated, it's giving us, we should start to see is that the error rate drops from the initial set of iterations through the kind of the lower set of iterations. And what I like to do, as Andy suggested, is also kind of use the quick graph tool to kind of see that error rate drop and kind of see how that's working here. So you can kind of see it's dropping, and then it hits a plateau and it drops again and continues to go down. This is set to 500 iterations. Maybe I want to beef this up to 1,000 iterations and plug that in as such. And what we're going to see is that, that graph, continue to flatten out like so. But we now have a start to something that we may want to then test some data with and see if we can predict the space classifications as it exists on this unlabeled data, right? We want to see if this is any good at telling a small office from a large office and so on. So what I'm going to do is I'm going to go down to this part of the graph where you can see that we're referencing in the layer called predicted. That's the unlabeled data. We are pulling out from this unlabeled data the dimensions of those spaces. So the dimensions of the space become our input, and then we're going to use the neural network to kind of understand the classification. So what I'm going to do is I'm going to go to the LunchBox tab, and under neural network, and maybe I'm just going to pause here and have a look at the questions. How to remove, how to find and remove outlier and training. That was from before. There's a question here that neural network training data takes a lot of time and is GPU intensive. What is the reason our network is trained so quick? Well, we're not using a whole lot of data. I think I think you indicated there less data, right? These neural networks, ACORD and all these things, are often trained on millions of data points. Here in this particular case, we're training it on, let's see, how many inputs do I have here? 72. So you can, I mean, and I think that's an important part to also consider, is that, we think about machine learning in the context of big data, and neural networks are data hungry. And the idea is that your predictive capabilities of your algorithms will improve, ideally, if you are able to supply it with more data and more accurate data over time. And also think about the feedback loops that Andy described, where you're adjusting your model based on new data that's always coming in. But you can, if you're dealing with some problems like what we're doing here, start to create semi reliable neural networks that you can test against, even with limited data. And I think that's an interesting challenge to think about, is the extent of your problem set, the complexity of your data to create an effective model. All that starts to play into how many neurons you need and how long it's going to take to process and crunch and all that good stuff. So yeah, this moved quite quickly. I'm going to go ahead and go to the machine learning tab, and we're going to do our neural network tester. And we're going to see how well this neural network is behaving relative to our trained data here. So I'm going to pass my neural network output from our neural network trainer into the neural network tester. It's then expecting input data that is of similar structure to how the inputs were trained here. So you can see I have two variables, length and width, that it was trained on. These are new length and width values that we're going to be providing into the input. And we're now getting a set of outputs. And our outputs are, and this is where things kind of get interesting when it comes to playing with how neural networks can be used as a classifier. We're getting a range of numeric outputs here. And what you're seeing is that these numeric outputs don't map perfectly to how we established these numeric outputs here in the training set, right? So we basically said small, medium, large are getting these particular values, right? 0.75, 0.25, and so on. And we're getting predicted data that is still constrained between -1 and 1, but we're getting values like 0.39, 0.23. you know, a little, you know, some a bit off, but still perhaps in proximity or within range of some of those initial values. So what we're doing here is we're now going to take this information that it's outputting, and we're going to remap it into discrete classifications of small, medium, large, and conference. So we have another C# component here that's going to take the numeric output, and instead of taking it to a discrete kind of numeric value, we're bringing it back to what it should be, which is small, medium, large, or conference center. And we're going to be using numeric ranges to do this. So you can kind of see that if you're getting a value of -1 to 0.05, it's going to label it small, medium, large, and so on. There's probably you know, a number of ways that you might go about, you know, doing something similar. This is a way that seemed to work quite well in this given scenario. But again, trying to get us back to that classification value. And I'm going to take this output here and plug it into the X input of this first C# component, and then I'm going to pass it into the value of this second C# component, which is also going to, you know, it does a similar set of operations, but instead of mapping it to the suite type, it's also mapping it to the kind of selections for cost for those suite types, right? What we can do now is actually go into Rhino and see how it's labeling this. And I think I may have had one small bug in the sample data that I sent along, or in the sample definition I sent along, and I'm going to ask you to maybe make a quick correction to your graph. There is a set of preview nodes inside of your Grasshopper definition that was taking the kind of area label and passing it into the location, as well as then this text information on the classification for text. I believe I may have given you flattened information going into this tag, which is kind of result in like text bunching up on each other. So I'm going to suggest that you graft your input here for the location value, which will help with the list management, and then also give you a display that looks something like this. And if we look through our building, what you're going to see is that it is identified this particular surface as being a medium size office. We can see a few large size offices in through here. We can see that we've got a small offices, and it's even managed to predict kind of a conference center, and that's because it's gone, it's identified these as being within a certain threshold here, even though we haven't explicitly trained it on any conference center dimension per se. But what I wanted to do is, if we go into Grasshopper again, we can see that we have a couple of semantic tools instantiated in our definition for writing properties. So what we're doing here is we've got a component that is going to take the result of this classification process and inject it into any given object's property set, and basically move this from an unclassified object into a classified one. So what I can do here is simply click on that button, and it's going to change up the coloring of our objects, and it's going to give us an attempt at how these objects should be classified, right? So now we're seeing that, okay, we identified these as mediums, we identified these as small, these as a conference room, and we've also then applied cost per square foot here. So we've taken, again, in my case, I took project B here, and I said, okay, well, let's map this into this unlabeled data, and this is what it was able to produce. Intuitively, if I look at this, it seems okay. But this is where we can actually start to play around with our input data, and also start to play around with how our network is working, and start to see the different outcomes here. What I'm going to do is I'm going to jump all the way back across to my input surfaces in this particular graph. And I'm going to grab the maybe just this project A here, and I'm going to go ahead and say set one, or select things first. And I'm going to say select multiple B reps, and I'm just going to select project A, and we're going to see if we get any kind of different variations in classification. Maybe we will, maybe we won't, depending on this example. Or earlier today I was getting some variations, but we'll see. Based on the parameters. So here you can see it did a little bit of a different classification. I don't know if you quite saw that, but in the previous data set I was working with, it had identified these as large offices. And then when I reran it on a different data set, it identified these as medium offices, right? And it had a, based on like those inputs, it changed up some of those results. And what I'm going to do is I'm also going to go in, and now I'm going to say set multiple B reps again. Actually, I don't want to use those. I want to right click, set multiple B reps. And then I want to select all of these projects together. Maybe, there we go. There we go. And I'm then going to I'm going to zoom in on my predicted output here. And I'm going to go ahead and reassign those properties. So yeah, we didn't see any change in that particular go around, but we understand that kind of different data sets may produce different results. And again, the idea being that the scenario I wanted to demonstrate was like, okay, well, I have all this existing data. Maybe this represents existing project data that you're collecting over time. Maybe it represents a set of design options that you've generated. And I want to then use those to train up a network to then kind of be a way to assign values to some other separate project. Andy didn't cover this aspect of the LunchBoxML nodes in his overview, but we're going to now kind of shift over and look at it here. We are in effect doing training and testing in a single graph in Grasshopper, right? So we have created a testing scenario up here with this object, with this component, and we're then doing, we did training up here, and then we're doing testing down here. Training and testing doesn't need to occur in the same Grasshopper graph. You may create a graph that's all about training. And then you might want to then save that neural network for future use in other Grasshopper contexts. So what we've done is we have provided this ability to, after you train up a neural network, you can right click on this node and choose, all right, I want to save my neural network. And so what I'm going to do is I'm going to go ahead and save this to a space type classifier, and I'm just going to call this space classification, NN, standing for neural network. And what this is going to do is it's going to author a .bin, a generic binary file that's going to save that neural network out, which means that if I then want to jump into a new Grasshopper document and I'm building up a parametric model elsewhere, I can start to pull in the pre-trained neural network that I had from another scenario. So I'm going to go ahead and go to, the Lunchbox tab, and I'm going to find under machine learning this idea of load saved model. So load saved model is going to allow me to identify a file path, and the file path is going to be pointed to our neural network file that was just saved out of the other definition. And wrong tab, Nate. There's the file path node. I'm going to right click on it. I'm going to say set one existing file. It's going to jump me out into the file explorer. I'm going to say, there's my neural network that I just trained up in some other context. I'm going to open that. I'm going to pass that in. And what it's going to do is it's going to identify that, you have a neural network here. And the neural network is now exposed as an object that I can start to use elsewhere. So there's my neural network, which means that I can go to the Lunchbox tab and find our neural network tester and start running tests on that neural network apart from the previous grasshopper definition. So there's a nice workflow opportunity here where as a designer or as someone who's building up different classifications, and sorry if you can hear my dog, he's kind of getting a little antsy in here, shaking around and such. Question, is it possible to save the neural network in .h5 format? We're saving it out using a using what's available in acord.net. So it's saving out the .bin file, which is how that particular framework saves out pre-saved neural networks. And Andy can answer more questions on that if he has any points.
Yeah, it's a simple binary format that it gets saved out to, and it's actually saving out the wrapper file. Well, this particular load save models component can deserialize both the naive Bayes neural network and also the SVM classifier. And so it deserializes it into specific LunchBoxML wrapper types as well. So it's not just your standard file that's being written out as a network. It's got some extra stuff that's being saved out into it. But yes, it's being saved out as just a bin file, which is a binary file writer, a standard binary file writer.
Cool. And as Andy indicated, he mentioned naive Bayes and support vector machines. This loader will not only let you load in neural networks, but it also lets you load in some of these other components. You can see we have an SVM tester. We also have a naive Bayes classification tester. This loader will recognize what type of machine learning scenario you're running on these pre-saved trained algorithms. Makes it pretty versatile. So I wanted to highlight this because what I want to do is I want to jump into the third example using the remaining time, which is going to build on this and start to introduce kind of two separate definitions. That one is used for training, one being used for the testing of the neural network. So I'm going to go ahead and open a document here. It's going to be in the examples under number 3. And it's going to be an occupancy value trainer to start. And since we are coming up at the 15-minute mark to the end of the workshop, I think is right? That sounds right. I might skip a few steps, but just know that there's a start and an end to these things. I might just simply skip ahead to some of these prepared examples as a demonstrator here. So I'm going to go ahead and open the occupancy value trainer. And the intent of this definition, you can see it's a bit messy. So sorry about that. Tried to at least group things together and kind of identify and leave notes in terms of what's what here. But what this definition is doing is it's essentially a desk calculator. How many desks can you fit within a given rectangular volume? You can see that we have different parameters for the desk length, desk depth, desk clearances, aisle widths, and so on. So if I were to change this to 6 feet for aisle width, we would see the parametric definition adjust versus 8. And maybe I want to increase the desk length to something like 8 itself. So it's going to increase the length of each desk, but then reduce the total number of desks, and so on. So we kind of have like just a very rudimentary, hey, I've got the space, I want to do an open office layout. What are the parameters here? There are 2 prepared solutions within this definition. One is like a standard desk layout. So if I go to a solution, you can see that we have this ability to restore state. So this idea of type packing, which I believe are the default ones that I set up. So there's much smaller desk sizes and far more people given the area. And there is then the solution of what we're calling the recognizing social distancing parameters, more area per person, so on. And this isn't using any kind of real world science. It's again just an example or scenario how this may in effect change our parameters and assumptions going into a new property that's commercial office. You can see it increase the amount of dimensions per person, increase like aisle widths and so on. So you end up having fewer desks in a given area than you would have under the previous set of assumptions. And we have these parameters for width and length and so on. And what I'm doing here is, in this particular example, is I want to create a training set that is going to be representative of the kind of dimensional inputs of a given space, and then try to predict how many objects I can fit inside of it based on this kind of known history of options that we may generate for this space, right? So if I go, for example, go over here and do I'm going to set this to say 25, which gives us nothing, by the way, which is actually kind of an important thing. If I go to 50, that's giving us a number of options there. And maybe I want to bring this down to 40, which shifts the orientation, that type of thing. What I'm going to do is I'm going to go I'm going to do an atypical use of Galapagos in a way. I'm going to use Galapagos as like an optioneering interface. It's not really going to be looking for optimums necessarily. That's not my goal. Essentially, I'm using it to iterate through various dimensions, excuse me, to construct my training set. So you can see I'm Xing out these recorded values, and I'm just going to open up Galapagos, and you can see it's set to maximize, which is not super important necessarily. And I'm just going to go ahead and run this as a solver. And what you're going to see is that as it's running the solutions, it's populating length and width and then desk count, right? So length and width of a given space are indicative of the inputs, the input structure, and then desk count is the output. So we can kind of imagine now downstream, this is going to be generating a set of options that we can use to train with. We're also, you can kind of see just kind of as a visualization here, this is also kind of plotting the options as well. So I'm just going to let this run for just 1 minute, and if there are any questions at this point before we go into the prediction part, I just wanted to demonstrate this. Okay. I'm just going to go ahead and stop this for the time being. It hasn't given us too many data points, but that's okay for right now. Because what we do have, I'm going to go ahead and hit stop here. Please stop. Okay, cool. So we now have this kind of an understanding of a sample set of data. So it's length, width, and then the kind of calculated desk count, and the calculation of the desk counts being derived by these formulas. So, and ideally would give us some more reliable desk counts, because we have this parametric model than if we were to say like square area per person predictions that we may use as a rule of thumb. But this setup is almost identical to what we've done before today, where we have the neural network set up, where we have some various hidden layers, hidden neurons. We're using resilient back propagation. This is something I like to do. I mean, if you're interested in kind of making snippets, code snippets for yourself, I used Grasshopper's drop-down menu component to allow me to quickly access some of these learning algorithms and activation functions. So as I start to work with these tools, that might be something you consider to do as well. Meta Hopper really lets you, is a plugin that lets you save these code snippets. So that's something to consider. But this is all set up as the training scenario, right? And what I've done and what I've provided in the sample data set that we've got is 2 pre-saved neural networks. I've run one neural network under the kind of tight packing assumption, and I've also run one neural network under the quote COVID-19 assumption for planning. So what I'm going to do is I'm going to go ahead and open up the other definition that's associated with this. So this is the trainer. I'm going to go to the occupancy value tester and assigner, and go ahead and go in, and looks like I may have a, that's fine, open the recovery file. That's fine. And what this is doing is it's taking the available, and maybe what I'm going to do here is under pipeline, I'm going to choose predicted. I'm going to enter in predicted here, which is going to take in this geometry for my predicted building, and the dimensions. Going to go through a very similar set of operations that you saw in the past example, where you have length and width. And then what we're doing here is we are then going to reference 2 pre-trained neural networks to create the prediction that we want. So we see we have a standard layout and a pandemic layout. Under the standard layout, I'm going to right click on this file path, and I'm going to choose one existing file. And I'm going to navigate to part 3 here, which is occupancy predictor. And you can see that we have 2 .bin files. One is COVID-19 and one is the standard desk layout. Since I've chosen the standard layout component here, I want to make sure I'm using the standard layout neural network, so there's not a confusion between the two. Hit open. And then under this one, I'm going to right click and choose the COVID-19 one. So I'm going to go ahead and click one existing file and select that one there. So here we now have a toggle. Currently there's a toggle here that lets me maneuver between the two. So if I have this set to false, this is going to use the standard layout neural network and switch between the file paths here versus if I wanted to do the COVID-19 layout. If I zoom in on this, you can see that everything is set to 0 at the moment because this is reading in the semantic properties. Remember when we first opened this file, if I click on any of these objects, we are getting desk layout, desk count standards, desk count standard, which is everything set to 0, desk count COVID-19, which is set to 0. What I need to do is, now that it's brought in the neural network that I've selected, I need to bake these properties into the Rhino model. You can see it's made some predictions here. I'm going to go ahead and you can see that there's a button there for write properties. And let me see if I can get some screen real estate going. I'm going to go ahead and write properties for that one. And then I'm going to, let's see if we're getting values coming across. Oh, we're getting some kind of wonky values. Wasn't doing that to me before. Well, this may have just blown up in my face. Let's see if it did, if it works on the other one. Ah. Hey, Andy, I wonder, I may need to follow up with everyone and reissue some different pre-trained neural networks, because I think maybe I accidentally shipped along or bundled up the previous iteration of the neural network node are results or pre-trained algorithms that were produced using the previous version of the neural network node? Do you think that would probably impact this?
It's possible.
Yeah, I might need to send along some an update to everyone with some updated pre-trained neural networks if you're looking to run this example. So apologies for that. I had tested this earlier and it seemed to be flying along just fine. I know that we only have like maybe 1 minute left. I do want to close the loop, and it's kind of like one of those, oh, and one other thing. And that's kind of the idea of just jumping everything into Revit, which isn't, it's sort of like a kind of a bit of an afterthought at this point, because the emphasis here really was the kind of more semantic oriented integration of data, along with the ability to train up neural networks and make predictions. But I did want to highlight kind of one possibility here when it came to the migration of data that has been assigned to various elements and moving that downstream into production. And so what you see here is we have a set of surfaces and we have data assigned to those surfaces. What I'm going to do is I'm simply going to go do what's called, if you have Conveyor, do a Conveyor setup. And what this is going to do is it's going to create the ability to tell different objects what they should be in terms of types, floor types, object types, and so on. Go ahead and hide this core here. And I'm simply going to select all my surfaces after the Conveyor setup is completed. You can see that we're getting a category of, I want to make these floors. I'm going to keep those at a generic 12-inch type. I'm going to go ahead and save my model. I'm going to jump over into Revit. Move zoom out of the way. I navigate to where I have this stuff saved, recognizing that time is of the essence. Saved right there at 3 o'clock. The Conveyor tool is going to recognize the various floor objects that have been assigned inside of Rhino. You do not need to save this. Thanks, Revit, for reminding me. And I'm just going to go ahead and load these in. And we can see where they're going to pop in. There we go. They're being built down here. So there we go. Yeah, coming along. Bit of a latency here, but it's building up, essentially bringing along each of these floors, drawing them as they existed in Rhino. And along with the creation of the floors, what we're going to see is that all the semantic properties that we've been working with when it comes to the object classification, even some of the internal Rhino areas and so on, are being generated and pulled along with these objects as we've brought them along. So it kind of starts to suggest potential data workflows for, as you go from design into production, being able to transfer these various properties over into the Revit environment. So that's completed. If I click on one of my objects and scroll down in the properties, you can see that we've got kind of the suite type being brought in, the Rhino computed area for the objects as well, cost per square foot, and what should have been our desk count predictions that kind of blew up in my face just there at the very end. Yeah, it's really what I wanted to highlight there was just a quick demonstrator of bringing that stuff across. And I know that we're just over time. Happy to take any final questions. And you can expect an update from us on some of those LunchBoxML examples.
Hi, Andy and Nate. Thanks a lot
Hey.
for an amazing workshop. I just had one question. So in the neural network training, is the architecture for the neural network sequential? And is it possible to like train for images or sequence like text data as well, like we do in convolutional neural network or something like
So I'm not sure I understand the first question when you talk about sequential. Are you talking about changing? So right now, are you talking about changing the number of hidden neurons in each layer?
Yeah, so I see like based on these variables, we have like the control of changing the number of neurons in hidden layers and
Correct.
yeah. So like, is it called a sequential neural network?
Is it called a sequential neural network? It's called
Yeah.
a feed forward, a multi-layer feed forward network. But one of the things we are talking about adding, I think right now Lunchbox is in a heavy sort of development phase where we're sort of modifying. Would be right now it's assuming that you have 3 layers or something like that, and you want the same number of hidden neurons in each of those layers. But I think what would probably be a better solution would be to have a list where you could have, 3 values. If you have 3 layers, you would have 3 values. Each, the first one would go for the first layer, second, and third. And so that way you could really specify the network architecture. You just have to make sure, that you understand what you're putting in. But I think that way you could really control, if you really wanted to try to modify the network architecture, you could do that. As far as as far as your second question with images, that is something called deep learning, and I think that's a separate topic that we haven't really addressed. You could begin to try to look at some of the examples in the Accord framework for deep learning. We have not tried to implement any of the deep learning algorithms yet in LunchBoxML. But it's definitely something of interest because I think when you start to get into images and training for that, you open up a lot of possibilities. Obviously, something that's been of interest to a lot of people has been the style GANs, and which are the adversarial neural networks, and so on. And so you could obviously start to apply those in different ways and come up with a lot of interesting techniques, which I think open a lot of creative opportunities. So look for that as new exploration, as I think it's something that we're interested in, but we just haven't exposed that just yet.
Thank you.
Any other questions?
Well, I really appreciate everyone coming. I kind of feel like it's an unfortunate state of affairs that we can't do these types of things in person and really have a chance to interact with you all both at breaks and at break time and after workshops and so on. But I hope everyone's staying safe and healthy. I hope you got something out of this workshop that can be used in your work. We're very excited about this. The idea of doing workshops like this is also gives us a chance to try out some new things that we may not be doing on a day-to-day basis. So very much appreciated, and thank you so much.